Alright, it's Niaki osteoson. So today we are going to have the Niaki chemistry series, and we are mainly focusing on redox reaction. So if you haven't subscribed to our YouTube channel, you need to do so so that you'll be notified whenever we post. So we are providing massive revisions, massive topical discussions in all the science subjects. We have a lot of tutors who specialize in different specialties. So we got you covered in all the science subjects. Both are for the O level and the A level syllabi, the ZIMSEC and the Cambridge exam board, right? So we want to dissect this topic. The term redox, it is made up of two ways. We're having reduction and we are also having oxidation. So we have two terms in this word, reduction and oxidation. So this simply means to say in a reaction called redox reaction, we're having these two processes, reduction and oxidation. So we want to explain what is meant by reduction and also what is meant by the term oxidation. As for now, we want to define the term redox, right? So a redox reaction is defined as a chemical reaction in which both reduction and oxidation are taking place simultaneously, right? So it is defined as a chemical reaction. It is a chemical reaction in which both reduction and oxidation occur simultaneously, right? So this is the definition for the redox reaction, right? So if you are to have one substance being oxidized, it simply means to say another substance must be reduced, right? So if we are having one chemical substance being oxidized, it simply means to say one. So we can say one must also be reduced. So this is the definition for the redox reaction. If we are having one being oxidized, we must have another one being reduced. So we want to define the terms reduction and oxidation. Reduction and oxidation. Are we together? So we want to define these two terms. So reduction and oxidation are complete opposite of each other, right? So if you know the definition of reduction, simply mean to say you are going to obviously know the definition of oxidation, right? Oxidation. So we want to use the table to differentiate the two, right? So they are defined in four aspects, right? So in terms of oxygen, reduction is defined as the loss of oxygen, and then here we are having the loss, right? Simply mean to say we are going to have the opposite here. So we are going to have the gain of oxygen, right? And then in terms of hydrogen, reduction, it is the gain of hydrogen. And then we're having gain here. It simply means to say we're going to have the opposite, which is the loss of hydrogen. And then we're having, we can define it also in terms of electrons. So reduction is the gain of electrons. It simply means to say oxidation is the loss of electrons. Are we together? So explain the concept of electrons, we can use this mnemonic which says oil rig. So it's oil rig, right? So rig is for reduction, right? So we want to have, so for oxidation is oil, right? And then for reduction is rig. So it's oil rig, right? So to explain this mnemonic, R represents reduction, I represents E. So its reduction is gaining in terms of electrons. And then oil its oxidation is loss in terms of electrons. So this is what you must know in terms of electrons. You must simply memorize oil ring to explain redox reactions in terms of the movement of electrons, the electron transfer, right? And then we can go on to explain using the oxidation states, right? So reduction is defined as the decrease or the decrement in oxidation state. And then our oxidation is defined as the increase in oxidation state, right? So these are the four aspects in which we are going to define reduction in oxidation, right? First we define in terms of oxygen, and then we go on to define in terms of hydrogen, and then electron transfer, and then lastly in terms of the oxidation states. Are we together? So what is the oxidation state? So let us say we're having the periodic table again. This is our periodic table. Alright, so this one is our periodic table, right? So the oxidation state is the charge on the atom, right? It is the charge, as per se. So it is the charge for you to understand, right? So you need to understand that it is the charge, right? The numerical number, what do you call that? Coefficient. So lithium, it is in group 1, meaning to say it is going to lose 1 electron, right? So it's plus 1. So the oxidation state is plus 1. And then beryllium, it is in group 2, meaning to say it is going to lose 2 electrons. The oxidation state, it is plus 2, right? And then we go on for oxygen, it is in group 6, meaning to say it needs extra 2 electrons. So the oxidation state, it is minus 2. So this is the oxidation state. So when we say oxidation, it is the increment in the oxidation number. We simply mean to say lithium. So these elements on the periodic table, the oxidation state is equal to 0, right? The oxidation state of uncombined elements is equal to 0. Let me highlight that one. The oxidation state number, or the oxidation number of uncombined elements is equal to 0. So all these elements, the oxidation states of these elements is equal to 0, right? So if we are to form the ions, we are either increasing the oxidation state or decreasing the oxidation state. So for lithium, originally it was 0, and then when we form the lithium ion, the cation, it is plus 1. So we are moving from 0 to plus 1, which is an increment in the oxidation state. And then for beryllium, the same thing, we are moving from 0 to plus 2, which is an increment. And then for oxygen, we are moving from 0 to minus 2, which is a decrement. So we have gained extra 2 electrons in terms of electron transfer, and then in terms of the oxidation state, we have moved from 0 to minus 2, which is a decrement in the oxidation state, which is defined by reduction. Are we together? So this is how you are going to understand this in terms of the periodic table, right? So we have other ions, which are the polyvalent ions, the radicals, for example, carbonate, sulfate, nitrate, hydroxide. So we're going to explain later how to figure out the oxidation states there, right? So we want to explain the effect of oxygen, right? So we said oxidation is the gain of oxygen, right? So let's say we're having the combustion of carbon to give carbon dioxide, right? So we're having carbon without oxygen here, and then here we're having carbon bonded to oxygen. So it is the gain of oxygen. Are we together? So this is the definition for oxidation in terms of the transfer of oxygen. And then we go on to define reduction in terms of oxygen, which is the loss of oxygen. So we are having the reaction between we can have the reaction between copper oxide plus carbon. So all the reactions in the blast furnace, some of the reactions in the blast furnace, so to give carbon dioxide. So as you can see here, copper is bonded to oxygen, but then here copper is not bonded to oxygen, meaning to say copper has lost this oxygen to carbon. So copper has been reduced, and then hydrogen has been oxidized. So it is a redox reaction. We are having both reduction and oxidation simultaneously in the same reaction, right? So this one has been oxidized, and then this one has been reduced. So you can explain by saying copper has lost its oxygen atom here, right? we are not having oxygen here. And then carbon is gained oxygen atom, we are having oxygen here. Are we together? So this is the explanation in terms of oxygen transfer, right? Because you can have the reduction of iron 3 oxide in the blast furnace by carbon to give iron plus carbon monoxide, and to balance we need a 3 here, and then a 2 there, and then a 3 here, right? So this equation is now balanced, right? So this is example of a redox. So iron has got its oxygen here, and then we are no longer having the oxygen here, right? So meaning to say iron has lost its oxygen, it has been reduced. And then in terms of the oxidation state, the oxidation state of iron was +3, and then here it's 0. So it simply means to say we are having a reduction in the oxidation state. And then carbon here, it wasn't bonded to any oxygen there, but as you can see here, carbon is bonded to oxygen, meaning to say it has gained oxygen, which is oxidation. Are we together? So this is what you must understand in terms of reduction in oxidation, right? This is what you must understand, right? And then we can also have the half equations of electrolysis. So we can have copper being oxidized to copper 2 ions plus 2 electrons. So copper, the oxidation state was 0, and then now it's +2, and then we have also lost the electrons, meaning to say copper has been oxidized. So these are the equations you must familiarize yourself with. Whenever you are given an equation, first identify the processes taking place. Where is the redox happening, and what is facilitating the redox processes. So we have these facts. We have the loss of oxygen, the loss of hydrogen, electrons, and then oxidation. You must understand all these aspects, right? And then we also need to calculate the oxygen states in the ionic compounds in the molecules, right? So let's say we are given copper 2 oxide. So right, let us say we are given this compound, and then we are told to calculate the oxidation state of copper. Calculate the oxidation state of copper. So what you are simply going to do here, we are simply going to name this one X, the oxidation state of copper X, which is the unknown. And then for oxygen, we know the oxidation state of oxygen from the periodic table. Oxygen is in group 6. It simply needs to have extra 2 electrons. So we are going to have this ion 2 minus. So the oxidation state for oxygen is -2. But for copper, we don't know the oxidation state for copper. So it's X minus 2 is equal to the overall charge for this ion. So it is equal to 0 since we are not having any charge there. So it is equal to 0. So it's X, linear equation, +2. And the oxidation state for copper is +2. Right? And then we can do the same in this compound. So it's ion. So we don't know the oxidation state for ion. So we want to calculate X, and then here is -2. So if you are given a compound, element in question is the one with the unknown, and then the other elements you can use the periodic table to deduce the oxidation states, right? You can use the periodic table to find the oxidation states. So here for ion we're having X, so we're having 2 atoms here, so it's 2X, right? And then here we're having 3, so it's 2 by -3, so it's +2 by 3 to give us the overall charge, to give us 0. So here is 2X plus -6 is equal to 0. 2x minus 6 is equal to 0, and then 2x is equal to 6 plus 6, and then x is equal to +3. So the oxidation state for ion is +3. And then we have this one, and then it's 2 minus. And then we are told to calculate the oxidation state for this chromium, right? So here is 2x, and then for this one it's -2, so it's -2 by 7, right? -2 by 7 to give us -2. This one, the overall charge for the ion, right? So we're simply going to carry out mathematical procedures, simple linear equations, right? So it's -14 is equal to -2, and then 2x is equal to 14 minus 2, and then 2x is equal to 12, and then x is equal to plus 6, right? And then we do the same for this one, right? So we want to calculate the oxidation state for this manganese, right? So we're simply going to have x plus, so here it's -2 by 4 to give us -1, this one here, right? So it's x minus 8 is equal to -1, x is equal to 8 minus 1, and then x is equal to +1, +7, I mean, right? So this is a simple simple linear equation. So this is what you are going to do whenever you are being examined to calculate the oxidation state for any given element within a compound. Right? So first you identify the element in question, right? And then you deduce the oxidation states of the other elements using the periodic table, right? So let us say given sodium hydroxide, so it's sodium, and then we are told to calculate the oxidation state for this sodium. So we know this one is -2, and then hydrogen behaves as a metal, a group 1 metal, right? Except in the hydrides when it is bonded to a group 1 metal. So in these compounds, hydrogen has got a charge of -1, right? So we're going to explain later, right? So here it's X, the sodium, -2 for the oxygen, and then +1 for the hydrogen, being equal to 0. So it's X -1 is equal to 0, X is equal to +1, right? And then we do the same for the sodium hydride. So it's A, then A, and then we want to calculate the oxidation state for hydrogen. So it's X. And then this one for sodium is +1. It's +1 plus X is equal to 0. X is equal to -1. Right? So the oxidation state for hydrogen in this compound, it is -1. Right? So whenever hydrogen bonded to the group 1 metals, it is going to have a +1 charge. And then we do the same for sodium for hydrogen peroxide. And then we want to calculate the oxidation state for oxygen. So it's X here, and then here it's 2. So it's +1 there, by +1. And then we are going to add 2x to give us 0. So we are going to have 2 plus 2x is equal to 0. And then 2x is equal to -2. And then x is equal to -1. So the oxidation state for oxygen in hydrogen peroxide, it is equal to -1. So this is how you are going to calculate the oxidation states for all the elements you are going to be examined on, right? And then what else do we need to understand on redox reactions? So we're going to explain much when we are doing the effect of transfer of electrons when we are going to do electrolysis, right? That's why you are going to understand the effect of electrolysis. So stay tuned to our channel so that whenever we post, you'll be notified, right? So we want to explain the oxidizing agent and the reducing agent, right? So a reducing agent, reducing agent is defined in three ways, right? So we can define a reducing agent as one that removes oxygen, right? One that removes oxygen. And then we can also define it as one which adds hydrogen to other substances. One that adds hydrogen to other substances, right? And then we can say here one that adds electrons, one that adds electrons to other substances. This is the definition for a reducing agent. So in other words, we are saying that a reducing agent at the end of the reaction, it is oxidized. At the end, it is oxidized. It reduces other chemical substances so that itself at the end of the reaction it is oxidized. So examples are for reducing agents. We are going to have all the metals, all the reactive metals, right? And then we can have carbon in the blast furnace, right? So from this equation here, right? So we are having carbon, and then we are having iron 3 oxide, right? So iron 3 carbon at the end of the reaction, it has been oxidized, meaning to say it has gained this oxygen, right? So it is a reducing agent. Why? Because at the end of the reaction, it has gained oxygen. It has been oxidized, right? It took oxygen from this iron 3 oxide, right? So it is a reducing agent. Are we together? And also we have hydrogen. Hydrogen can also act as a reducing agent, and etc. Right? So these are examples of a reducing agent, right? And then we also have to define the term in oxidizing agent. Oxidizing agent. So an oxidizing agent can be defined as one which adds oxygen to other substances, and then 1 which removes electrons, removes electrons from other substances, right? And then we can also say 1 which removes hydrogen from other substances, right? So this is the definition for an oxidizing agent. So we're having this equation again. So it's iron 3 plus carbon monoxide to give iron 2 plus carbon dioxide. So we can have 3 moles here, and then we can have 2 there, and then we can have 3 here to balance the equation, right? So here we're having carbon monoxide which is oxidized to carbon dioxide. So we're having 1 oxygen atom, and then here we're having 2, meaning to say we've gained another oxygen atom. So this one is a reducing agent, and then this one is the product of reducing agent, meaning to say we're having carbon monoxide being oxidized here, and then here we're having oxygen, and then here we're no longer having the oxygen, meaning to say this one has been reduced. So this one is the oxidizing agent. Why? Because at the end of the reaction it is reduced. So an oxidizing agent at the end of the reaction it is reduced, and then a reducing agent at the end of the reaction it is oxidized, right? So this one is the reducing agent. Why? Because at the end of the reaction it is oxidized. Are we together? So this is what you must understand in terms of oxidizing and reducing agent. And then examples of oxidizing agent, we can have potassium dichromate, right? And we can also have potassium permanganate. Are we together? And then etc. We can have the halogens, we can have oxygen, and etc. Right? So for us to deduce whether this one is an oxidizing agent or whether this one is a reducing agent, you need to understand the mechanism of the reaction. You need to stick to these facts, right? Gain of oxygen, loss of hydrogen, loss of electrons, and then increment in the oxidation states. Are we together? So this is what you must understand in terms of redox reactions. And then we have the oxidizing agents, the potassium dichromate and the potassium permanganate. So we are going to explain these when we are doing organic chemistry. So for potassium dichromate, the initial color it is orange, and then the final color changes from orange to green, right? And then this potassium permanganate, the initial color it is purple, and then it changes to colorless. So we use these reagents when testing for reducing agent. Since these are oxidizing agent, when they react with reducing agents, we are going to observe these color changes, right? So at times they can say you are having sulfur dioxide. So this is the change we are going to have from purple to colorless, and then here from orange to green, right? So for the oxidation states of the ions, you mustn't concentrate much on that because it's A-level transition elements. For you guys, you need to understand that we use these reactions to test for reducing agents, right? And also you can use it to test for organic chemistry, moving from alcohols to carboxylic acids, right? So this is the test whereby we can use this one, and then for the oxidation of aldehydes and etc. So for you guys, you need only to appreciate the color change, and you're done. Are we together? So this is what you must know in terms of redox reaction. As I've alluded to before, this is a very, very easy topic, right? This is a very, very easy topic. Are we together? So we are now moving on to the next topic of our series, right?